The chemical equilibrium section of the chemistry paper starts with multiple choice question 1.6, which reads, consider the equilibrium represented by the balanced equation below. Which one of the following changes to the equilibrium will favor the forward reaction? And there are two factors that we are changing here. The first is temperature, where we are going to refer to the enthalpy change that's given to us that tells us the enthalpy being negative means that the forward reaction is exothermic, meaning the forward reaction heats up. And the second change that we are going to be making is to the pH, where we know pH is about the hydrogen ion or the hydronium ion concentration, where a higher hydronium ion concentration or hydrogen ion concentration means a lower pH. And so the changes that we can make here, we know that in order to favor the forward reaction in terms of temperature, by Le Chatelier's principle, if we wanted to favor the forward reaction, which is exothermic, we would have to cool this reaction down, because by cooling it down, Le Chatelier tries to counter that change by heating itself up, thereby favoring the forward reaction, which is exothermic, which means that our option in terms of temperature change is either decreasing the temperature or is only decreasing the temperature, meaning option A or option B. The next change is changing the pH, where what we need to do is we want to favor the forward reaction. What we can hopefully see here is that there are hydrogen ions present in the reactants on the left-hand side of this reaction. And so if we want to favor the forward reaction, that means that we want to favor the direction that uses up this hydrogen ion. And that means that what we would need to do is we would initially want to increase the hydrogen ion concentration, basically because by Le Chatelier's principle, if I increase the concentration of one of the reactants, we will favor the forward reaction to try to counter that change. Now, increasing the concentration of hydrogen ions, we know is going to make the solution more acidic, which is actually going to make the pH of the solution decrease, because the pH, as it becomes more acidic, heads away from 7 more towards 0. And so what we're looking at here is we're saying that option B is the correct option, because decreasing the temperature will favor the forward reaction, which is exothermic, and decreasing the pH would mean adding more hydrogen ions, which again would favor the forward reaction. And so we can then say that our correct answer is option B. Question 6 reads, the dissociation of iodine molecules to form iodine atoms is a reversible reaction taking place in a sealed container at 727 degrees Celsius. The balanced equation for the reaction is given, and Kc for the reaction at this temperature is also given. Write down the meaning of the term reversible reaction, and there are a number of different ways to define a reversible reaction, but anything along these lines where we say that it is where the products can be converted back to reactants, or both the forward and reverse reactions can take place, or a reaction that can take place in both directions. Question 6.2. At equilibrium, the pressure in the system is increased by decreasing the volume of the container at a constant temperature. 6.2 then goes on to ask, how will each of the following be affected? Choose increases, decreases, or remains the same. And 6.2.1, the value of the equilibrium constant, where immediately we know that the only change that affects our equilibrium constant, Kc, is a temperature change. So what they have done here is they have decreased the volume and therefore increased the pressure, but importantly, that has happened at a constant temperature, and therefore our equilibrium constant, Kc, will remain unchanged. And so our answer for 6.2.1 is that the equilibrium constant remains the same. Again, the only change that can affect our equilibrium constant is a temperature change. Question 6.2.2, the number of iodine molecules, and the iodine molecules we can see are on the left-hand side of this reaction. What's important for us to do here is to realize that by counting the molecules on either side here, we can see that an iodine molecule means that on the left-hand side of this reaction, there is only one molecule, where on the right-hand side, there are two molecules. So what we are doing by decreasing the volume, the first thing that we do is we decrease the volume, which therefore has a result that it increases the pressure. Either way, what we are saying is there is now less space available for the molecules, and Le Chatelier's principle tries to counter this change by favoring the direction that undoes that. And so when there's less space available, the reverse reaction is going to be favored because the reverse reaction produces fewer molecules. It produces only one molecule as opposed to two. And so as a result, we are going to favor the reverse reaction, and therefore our number of I2 molecules, the answer to question 6.2.2, is going to increase. Question 6.3, explain the answer to 6.2.2 by referring to Le Chatelier's principle. And so what we're going to start out here by doing is we're going to say that a pressure increase is going to, by Le Chatelier's principle, a pressure increase is going to cause Le Chatelier's principle to favor the direction that produces fewer molecules, favor fewer molecules. Because we have increased the pressure, Le Chatelier's principle is going to favor the direction that produces fewer molecules, and therefore the reverse reaction is favored. Question 6.4. At 227 degrees Celsius, the Kc value for the reaction above is 5.6 times 10 to the negative 12. Is the forward reaction endo or exothermic? And fully explain your answer. So what we've got here is we've been given our Kc value at two separate temperatures. The one at 727, which is 3.76 times 10 to the negative 3. The second one is at 227 degrees Celsius, and that is 5.6 times 10 to the negative 12. So what we can see here is that the equilibrium constant, our Kc value at a higher temperature, is far bigger than the equilibrium constant at a lower temperature, 10 to the minus 3 compared to 10 to the minus 12. What's important for us to see here is that our Kc expression is always the concentration of our products over the concentration of the reactants, or in this case, specifically, it is the concentration of our iodine atoms over the concentration of the iodine molecules. And so what we need to see is we need to see that by Kc increasing, I'm going to look at it from the 227 to the 727. What we have done here is we've increased the temperature by 500 degrees Celsius. An increase in Kc, in that increase in temperature from 10 to the minus 12 to 10 to the minus 3, implies that the concentration of iodine atoms has increased while the concentration of iodine molecules has decreased. Because this fraction has gotten bigger, it means that the numerator has increased and the denominator has decreased. What that tells us is that we have favored the forward reaction. The forward reaction has been favored because we've produced more iodine and less iodine molecules. We've produced more iodine atoms and fewer iodine molecules. So what we can now say is that an increase in temperature has produced a favoring of the forward reaction because we have increased the concentration of iodine atoms and decreased the concentration of iodine molecules. So we favored the forward reaction. And now finally, we need to see that when we increase the temperature, we would typically favor the endothermic reaction by Le Chatelier's principle. An increase in temperature would encourage us to, or encourage the reaction to try to undo that change, therefore favor the endothermic reaction, and therefore we can say that since the forward reaction was favored with an increase in temperature, the forward reaction must be the endothermic reaction. Question 6.5 reads, a certain mass of iodine molecules, I2, is sealed in a 12.3 cubic decimeter flask at a temperature of 727 degrees Celsius, where our Kc value is given. When equilibrium is reached, the concentration of the iodine atoms is found to be 4.79 times 10 to the negative 3 moles per cubic decimeter. Calculate the initial mass of the iodine molecules in the flask. Now, this question has a number of ways that it can be solved, but the most common one is to use what is either called a Schreck or an ice table. And we do that by starting out with the one calculation that we can do, where we start out with our Kc expression, where we know that Kc for this reaction is going to be our concentration of the iodine atoms to the power of its exponent, divided by the concentration of the iodine molecules, where the concentration of the iodine atoms and our value for Kc is given as 3.76 times 10 to the power of minus 3. Our concentration of iodine atoms is also given to us at equilibrium, which is 4.79 times 10 to the negative 3. And that then leaves our concentration. We must remember to square that concentration of the iodine atoms, and our concentration of the iodine molecules at equilibrium is unknown, but it's the only unknown in this equation, and therefore we can solve to find that concentration at equilibrium to be 6.102 times 10 to the negative 3 moles per cubic decimeter. We can then set up our Schreck or ice table, where we say that our initial amount at the start, or initial, in a number of moles is then compared to the amount that is reacted, or the amount that reacts, also in moles, and then that finds our amount at equilibrium, again, in a number of moles, and then the final concentration at equilibrium, that being in moles per cubic decimeter. That given for this reaction, which is the reaction of iodine molecules to iodine atoms. And we can now fill in the values that we have, where we have now the equilibrium concentration for each of these, where our equilibrium concentration of iodine molecules is 6.102 times 10 to the power of negative 3, and our equilibrium concentration of iodine atoms is the given value of 4.79 times 10 to the minus 3. We can then use the formula that is given to us, where once we know the molar gas volume and we know the concentration, once we know the concentration, we know the volume, we can say that our number of moles is equal to the concentration multiplied by the volume, where the volume is given to us as 12.3, and our concentration for each of these is known, which means then that we can find our quantities at equilibrium. For our I2, it is 0.0751. We don't round to 2 decimal places while we're busy with the calculation, and our number of moles of iodine is then 0.0589 moles. Then we use the information that we initially have, where we were told that a certain mass of iodine molecules is sealed in a container, and we are told, or by inference, we can then see that that means that there are no iodine atoms in that initial container, which means that if we started with 0 iodine, we ended with 0.0589, that means that we must have formed 0.0589 moles of iodine in this reaction. And then because we know that the ratio of iodine molecules to iodine atoms is 2 to 1, if we formed 0.0589 moles of iodine atoms, we must have used up half of that, 0.0295 moles of iodine. And then finally, what that tells us is that we must have, if we started or if we ended with 0.0751 moles after having used 0.0295 moles, that must mean that we started initially with 0.1045 moles of iodine. And the question has asked us what mass of iodine, and so we can say that our mass of iodine that was sealed in that container is equal to the number of moles multiplied by the molar mass, that is 0.1045, multiplied by the molar mass for iodine, which is 254, which then tells us that our initial mass of iodine must have been 26.54 grams. And so just to walk through that calculation once again, we use the given value for the Kc at this temperature of 3.76 times 10 to the negative 3, along with our expression for Kc and the concentration of the iodine atoms at equilibrium, which is given to us to find our equilibrium concentration of iodine molecules. What that allows us to do is it allows us to set up what is either called a Shrek or an ice table, where we can say that at equilibrium, the concentration of iodine molecules is 6.102, this value that we've just calculated using Kc. And the value of the concentration of iodine atoms was given to us in the question, 4.79 times 10 to the minus 3. Because we then know the volume of this container, we can then multiply the concentration by the volume using this formula here to find the number of moles of each of these substances at equilibrium. Once we have those values, because we know that we started out with 0 iodine atoms, we were told that this is sealed in a container, that means that we must have formed 0.0589 moles of iodine, which means that in order to form that, we must have, using the ratio of iodine molecules to atoms, we must have used up 0.0295. And then because we know that we ended up with a certain number of moles and we know how many moles we used, we can add 0.075 to 0.0295 to find our initial number of moles of iodine. And then finally, with that initial number of moles, we use the formula mass is equal to number of moles multiplied by the molar mass calculated as 254. And therefore, our initial number of moles, or our number of grams, was 26.54. A question like this, marked according to the guideline document, the meaning of the term reversible reaction, because it is not a definition as required by the guideline documents, there are a number of options that are accepted as correct options for that question. 6.2.1, there's one mark for noticing that Kc only changes when the temperature changes. This pressure change, therefore, means that Kc remains the same. 6.2.2, the number of iodine molecules will increase, and the explanation given there were 2 marks allocated for that, and those marks were one for saying that when we increase the pressure, we favor the side that produces fewer molecules, and the second one for therefore saying that the reverse reaction is favored. Question 6.4 is a 4-mark question that requires a longer explanation, where we started out, our first mark was for explaining that Kc increases with an increase in temperature. That's what we've noticed from this part over here. When the temperature increased, Kc increases. What we could then say is we say, therefore, the forward reaction is favored. And there was a mark allocated for that, for saying or realizing that this means that the forward reaction is favored because the concentration increases. That was our second mark there. The third mark was then for saying this must mean that the forward reaction is the endothermic reaction. And then the fourth mark was for giving some kind of explanation relating to the concentration changes that led us to understand that the forward reaction is favored. Question 6.5, there were a number of options for how to solve this question. There was 1 mark given for correctly writing down the expression for Kc for this reaction and correctly substituting in the correct values in the correct places. What this then allowed us to do is it allowed us to use our concentration to use the volume of the substance along with the concentration to calculate the number of moles of each of these at equilibrium. So there was 1 mark for that calculation, whether it was done in the table or outside of the table. Using that, we were then able to determine the number of moles of each substance that reacted. And once we had done that, and especially using the ratio, where there was a mark allocated for the use of that ratio, once we had done that, there was a mark for calculating the number of moles of substance produced, and then a mark for calculating the correct number of grams. And that then finds our 1, 2, 3, 4, 5, 6, 7, 8, 9 marks for this question. Again, there were a number of ways to do this. It could also have been done by using a variable x in this table. And then with that variable x, we could find an equilibrium concentration with an expression in terms of x, and then substituting that expression into our Kc value. Again, the result and the mark allocation would have been exactly the same.